Hey guys, Dr. Thomas. It is chapter 13, slide 21 of the PowerPoint. We're getting into the math section of chapter 13 for really pretty much the rest of the chapter. We have to start out by introducing, in 1211, we really focus on one type of concentration from chapter 4, and that is molarity. That is the most commonly used concentration unit in chemistry. But there are cases where we need to express the concentration using different units. So on slide 21, it goes through these. Of course, the first one is molarity. It is represented with a capital M, and it represents moles per liter. I'm not going to do any problems with that one because I'm going to assume that you know that pretty well from chapter 4, 1211. If not, go back and practice those. But a new concentration unit for us is molality. Molality is represented with a lowercase m. So if I write little m, the units that we use are the moles of solute over the kilograms, specifically of the solvent. This is something a lot of people miss on the test because if you're not paying attention to details, most of the concentration units in the bottom, we are talking about the solution as a whole, but when we do molality, it is the kilograms of just the solvent that we put on the bottom. So make sure you pay attention to that. We will work some problems with that in a little bit. The next concentration unit is mole fraction. It's represented by the Greek letter chi. If a solution contains two things, the solute and the solvent, we can calculate the mole fraction for both of those. Mole fraction is really the only one that we would commonly find the mole fraction of the solvent. All the other ones tend to focus more on the solute in terms of, like, when you look at a bottle in lab, it's always going to have the concentration of HCl or the concentration of sodium chloride or the concentration of phosphoric acid or whatever. Those are always the solutes. That's what's always given on the bottle, assuming that there's a bunch of water in there, but we want to know how much solute's in there. Okay? With mole fraction, it can be either component, solute or solvent. So let's just say a solution is made up of compound A and compound B. The mole fraction of A is going to equal, it's going to be the moles of that component. So the moles of A over the total moles of everything in the solution. So again, if there's only two components, that means the bottom would be the moles of A plus the moles of B. If there were three components, it would be moles of A plus moles of B plus moles of C on the bottom. It's just the sum of everything in the solution, all their moles together, and then the one component on top is the one that we're interested in. Okay? You could write the mole fraction for compound B exactly the same way. It's just on top, I would have the moles of B here instead of the moles of A. Okay? Again, we'll work problems with that as we go along. The next set of concentrations, there are three of them listed on the PowerPoint, are percentages. There's percentage weight to weight, which is also called percent mass to mass sometimes, or if they say the mass percentage. Those are all the same thing. That is typically, let's say it's percent mass to mass is how it's written. That is going to be the grams of the solute over the grams of solution times 100%. So again, mass to mass is grams to grams. We could do that with kilograms to kilograms or pounds to pounds. Any mass unit would be fine as long as it's the same on top and bottom. Okay? The next one is, actually that was the second one. The first one it lists is actually percent weight to volume or percent mass to volume. Again, for all the percentages, we tend to use grams as our mass unit. So it'll be grams of solute on top. And then on the bottom, if we have volume, it's kind of important to know that the scale, a gram of something, and if assume we're talking about an aqueous solution, 100 grams of a solution is usually about 100 milliliters. So those two unit values are comparable to each other. So if we're going to use grams on top, we use the comparable volume measurement on the bottom, which is milliliters. So it'll be grams of solute over the milliliters of solution times 100. And then finally, the third one that I'm not going to write up here is percent volume to volume. Same kind of setup. It's going to typically be milliliters of the solute over milliliters of solution times 100. So they're all very similar in how we set these up. The cases where you use these are often used outside of chemistry, maybe in the medical field. If you go to the hospital, you're dehydrated, and they put you on a saline solution, IV, the salt in the water that they're putting in the IV and putting into your body is 0.9% mass to volume, sodium chloride. Basically, that's a measurement that we don't really need any chemistry knowledge to understand percentages and a mass to volume. We would just know that if they wanted to make 100 milliliters, percentage is always parts out of 100. That would be 0.9 grams of NaCl per 100 milliliters of solution. That is the ratio of sodium chloride to the volume of the solution that has to exist in that solution being used for IV. Now it's important that concentration has to be right, because if they give you a solution that's too high in salt, it can actually cause problems. It can dehydrate your cells. Again, osmotic pressure comes up later in the PowerPoint. But if it's too salty, it can kill you. If there's not enough salt in it, that can also cause some health problems. So either way, they have to have the right concentration, and the concentration is always going to be this ratio. Now, let's just say a hospital, there's an emergency, they need lots of saline solution, and they have to make it themselves. Well, if they have some distilled water and some salt, they could use this concentration to calculate how much is needed for a larger volume. Let's say I need to make 500 milliliters of this solution. Well, if it's 0.9 grams to 100 milliliters, then I could set up a proportion and say, how many grams do I need in 500 milliliters? So it'd be 0.9 over 100 equals X over 500. I could solve for X there and figure out how much salt needs to be measured out to make that solution. Okay? So this is more of just a mathematical relationship, not really any chemistry involved. We're not getting into moles and that kind of stuff. So it's a useful unit outside of chemistry. Also, percent volume to volume. If you ever have an alcoholic drink, the amount of alcohol in a drink is measured in proof. If you buy a bottle of tequila, typically that is the amount of alcohol is 80 proof. The proof of alcohol is double the percentage. So if tequila is 80 proof, that means it's 40% ethanol. That's actually a volume to volume measurement, because ethanol is a liquid, you're dissolving it into water, which is a liquid. So it's 40 milliliters of ethanol per 100 milliliters of tequila. That's where the 40% or the 80 proof comes from. Okay? So these are very common units used in everyday life. And then finally, the last one on the slide mentions ppm. ppm stands for parts per million. That is a unit that is used specifically when we have really low concentrations. Often when we're talking about toxic materials, the EPA, if they're measuring samples out in the environment, and they want to know, if they think there's lead in the water, it only takes a little bit of lead to make the water toxic for us to drink. So with very small numbers, ppm or even ppb, which would be part per billion, and even at times ppt is parts per trillion, those units are useful. The key on those units, when you set them up, there's a couple of different approaches you can do, but the one that I prefer, ppm, parts per million. A million stands for 10 to the 6th. So I want to pick two units that are separated by 10 to the 6th. So let's just say I measure my solute in milligrams. The unit that's 10 to the 6th bigger than that is kilograms. So basically, 1 ppm would be 1 milligram of the solute dissolved into a kilogram of the solution. 25 ppm would be 25 milligrams to 1 kilogram. Okay? Now, those units are not locked in. I could do the same idea. I could do micrograms per gram. Again, those two are separated by 10 to the 6th. So as long as the units are separated by 10 to the 6th, the ratio works to make it ppm. Now, milligrams per kilogram is probably the most common, although I will say they won't always write it like this because just like we've said before that a gram is equivalent to a milliliter in an aqueous solution if the density is about 1. A kilogram of solution is actually pretty close to equivalent to 1 liter if the density is nearly 1 gram per milliliter. So instead of writing milligrams of solute per kilogram, sometimes they're going to write milligrams of solute per liter. That is also a representation, just like this one. I'm just replacing kilograms with a unit that's pretty much equivalent to it, which is liters. Okay? And since we're talking about low concentrations here, these are usually very dilute aqueous solutions. And as dilute solutions, the density usually is really close to 1 gram per milliliter. So that makes that a good assumption. Okay? So those are our concentration units. I'll mention, so ppm, I want to separate my units by 10 to the 6th. If I do ppb, I would separate by 10 to the 9th. So that could be micrograms per kilogram, or it could be nanograms per gram. Either one of those would be okay. All right, so let's get into the next slide. So slide 22 has a series of molarity problems. Again, you should be familiar with those. I'm not even going to go over those because that's stuff that you should be able to do relatively easily. If you can't do those easily, then you definitely need to go back and practice. Come get help if you need to. But molarity problems are pretty basic. We need to be able to fly through those every time. So now we're on slide 23. We'll do a few of the percentage calculations. I think I'm going to do the first one, the third one, and the fifth one. So the first one says if 6 grams of sodium chloride are dissolved in enough water to make 300 milliliter solution, calculate the percent weight to volume of the sodium chloride in the solution. So percent weight to volume, we know it should be grams of the solute, which will be the sodium chloride, divided by the milliliters of solution, times 100. So if I just plug my numbers in, it was 6 grams of sodium chloride to 300 milliliters. 6 over 300 times 100 should give you 2%. Sig fig wise, really the 300 milliliters only has 1 sig fig, so I should write that as 2% weight to volume NaCl. That is the information I should write down for my answer because, again, my answer has to have units. We need to be specific. If you're talking about a percentage, you need to tell me which one it is, and then obviously you should identify what your solute is. So this is 2% weight to volume NaCl. All right, that's the first one. Then we get to the third problem. .500 milliliter solution contains 25 grams. Actually, I don't want to do that one. Let's do the second one instead. A solution is prepared by mixing 15 grams of sodium carbonate and 235 grams of water. Calculate the mass percent. So percent mass to mass, or percent weight to weight. It's going to be the grams of the solute, which the solute on top is going to be the sodium carbonate. So 15 grams of Na2CO3. On the bottom should be the grams of solution. On the test, many people will miss this problem because they'll just look at the 235 grams of water and throw that on the bottom. The mass percent has to have the mass of the solution on the bottom, which is the solute and solvent together. The masses have to be combined, so 15 plus 235, it should be 250 grams on the bottom of solution times 100, and then that would be your percentage. Again, whatever your answer is, 15 over 250, I want to say that's 6%. That should be 6%, probably 6.0% mass to mass, Na2CO3. Okay, so that's that one. And then finally, let's do the last problem. How many grams of sodium hydroxide are needed to prepare 2 liters of a 12% mass to volume solution? So for that one, I could set up the formula, percent mass to volume equals mass over volume times 100. I could plug in the percentage on the left side, plug in the volume in the bottom, and solve for the mass. That's one way to do it. I'm going to do it more dimensional analysis method. I have 2 liters of solution, and I want to know the grams of sodium hydroxide. Now, the percentage, it says it is 12% mass to volume. That means it's 12 grams per 100 milliliters. Since my volume and the percentage is in milliliters, I need to switch my liters into milliliters before I can use it. So my first step, 1 liter to 1,000 milliliters. So 2 times 1,000, it's going to be 2,000 milliliters of solution. Then I can say my percentage is 12%. So that's going to be 12 grams of NaOH per 100 milliliters of solution. Milliliters cancel milliliters. So if I do 2 times 1,000 times 12, that should give me 240. Wait. Oh, hold on. Let's see. I forgot to divide by 100. So 240. So it's going to be 240 grams of sodium hydroxide. That's how much I would have to add. Put it into a flask, fill it up to 2 liters of solution. That would give me the concentration that I need. All right, so now slide 24. We're getting into problems that are a little bit harder, using some of the concentration units that we haven't seen before. So I want to find the first problem, the mole fraction of potassium iodide in a solution prepared by dissolving 5 grams of Ki in 50 mils of water. So I have 5 grams of potassium iodide, 50 milliliters of water, and I want to find the mole fraction of Ki. Okay, again, you cannot work these problems if you don't know the units of the concentration. So mole fraction, I'm going to need to have on top the moles of Ki. On the bottom, it's going to be the moles of Ki plus the moles of water. Okay, so the moles of Ki, well, I know I have 5 grams. The atomic weight of potassium is 39.1. Molecular weight of iodine is 126.9. So if I add those together, molecular weight is 166. So I'm going to do 5 divided by 166. So 5 grams divided by the molecular weight. That's going to give me 0.03012 moles of Ki. So that number is going to go right there. And I'm going to put it in the bottom. I'm going to use the moles of Ki twice. For water, there's 50 milliliters. I know the density of water is 1 gram per milliliter. So 50 milliliters, I can switch that into 50 grams. And then divide by 18 is the molecular weight of water. So 50 over 18 is going to give me the moles. That's going to be 2.778. That number is going to go right here. So I'm going to have basically 0.03012 over 0.03012 plus 2.778. and I got that the mole fraction of Ki is 0.0107. Again, sig fig wise, it has 2 sig figs. So I'm going to write my answer. The mole fraction of Ki equals 0.011. Now, this is a ratio, moles over moles. Since the moles cancel, mole fraction doesn't have any units, but I am a little bit picky about how you write it. You don't never report an answer as just a number without telling me anything about it. So specifically, I want you to write the symbol chi, which is like a capital X, pretty much. But the mole fraction of Ki equals 0.011. Now, a trick about mole fraction, if they asked you for the mole fraction of water, the mole, kind of like if you have 2 percentages, percentages always add up to 100. So if one percentage is 40%, the other one has to be 60%. With mole fraction, they always add up to 1. So if the mole fraction of Ki is 0.011, if I wanted the mole fraction of the water, I know it's going to be 1 minus that. So that's going to give me 0.989. Or I can round that to 0.99. But either way, those are the mole fractions of both components in the solution. Question only asks for the first one, but if needed, the second one is easily found. Okay? Videos get long. I'm going to cut it off. I'll pick back up on this slide in the next one.